Hey there, welcome to a video discussing the second half of part 2 of the notes for our polar unit. Here we're picking up at the bottom of page 12 on cardioid curves. We didn't talk about this in class last time. So what we're going to do when we go about these graphs, we're going to set our lowest theta to 0 and our highest theta to 2 pi. You'll want to do that in the TI-84 calculator. Of course, we punch in Desmos. It's real easy, just does it for you. We're going to consider the following four polar functions: r equals 1 plus cos theta, r equals 2 minus 2 cos theta, r equals 3 plus 3 sine theta, and r equals 4 minus 4 sine theta. So if you graph these in your calculator and do a sketch, labeling these three key points, let's do the first one. R equals 1 plus cos theta. So I'll go to my calculator, turn on, go to mode, make sure radian is selected, and switch to polar. Go to y equals, oh, don't know why didn't do that. Let's try it again. Hit enter. There we go. Got to hit enter a little more carefully. So 1 plus cos theta, 1 plus cos theta. And graph it. So we get ourselves, it kind of looks like a circle, but it's not really a circle. So let's actually change this up. So 0 to 2 pi is set. We'll make that 0.1, just a little bit more standard step. Let's actually reduce this to, say, -3 to 3. And also -3 to 3. And you see there's a bit of a divot at the pole. And that's called a cardioid because it kind of looks like a heart a little bit. You could totally make a table and plot some points, plug in different values of theta and see what the R values are. But we expect the curve to touch the y-axis, or I guess at theta equals pi over 2 at 1 and -1. And also we do see a point at radius of 2 and at theta of 0. So actually I could do probably a quick table here. R and theta. So again, if theta were 0, we do get 2. So that makes sense, right? If theta were pi over 2, we get 1. So that makes sense that we get a point over here. And if theta were, say, 3 pi over 2, or sorry, we'll say pi, you do get 0 for the radius there. 3 pi over 2, you get 1 again, because cosine of 3 pi over 2 is 0. And again, we have a point at the pole at r is 0 at pi. So the graph will look kind of like this. It kind of has this little divot, does that, and does that. I know it's not the best looking cardioid, but not quite what you see in the calculator, but that's what you get. Now, for the other one, I'll avoid doing the calculator just in the interest of time. But again, if I make a quick table here, if I were to plug in 0, I do get 2. Actually, is that right? No, I get 0. If I plug in pi over 2, I do get 2. That makes sense. If I plug in pi, actually I get -4. No, I get 4. My apologies again. I get a raised to 4 when I plug in pi. If I plug in 3 pi over 2, I should get 2 again. So raised to 2. Okay. So all makes sense. So again, let's actually, we probably should be doing is try to make a polar coordinate system here. Should be doing that, to be honest with you guys, or using polar paper. So 0, 0, right there. Pi over 2 and 2, right there. Pi is a 4, a circle of 4, raised to 4. 3 pi over 2 is at 2. So the cardioid is going to look like this. So it has this little divot in the middle. I know I didn't quite show it the best I could, but it's kind of like that. That's a little bit better. That's what you would get. I did 4 key points here. The intercepts with the theta equals pi over 2 line, the pole, and then obviously at over here at 4 comma pi. So that's what we get there. And then finally for the other 2 graphs, I'll try to do this a little more quickly. You have -3 and 3, and it's going to hit 6, by the way, because if I do plug in pi, 3 plus, pi over 2, you get 3 plus 3, which is 6. It does hit 6. It's going to hit the pole as well, especially when theta is 3 pi over 2. And of course, if I plug in 0 or pi, I get 3 for r. So the graph will look like this. And then lastly, for this one here, this will be opening down. Again, plot points if you like. It hits -8, by the way. So if I plug in, sorry, not -8. If you hit 3 pi over 2, you get 8. So 8 comma 3 pi over 2 will be a point on that curve. And it'll definitely be a point at the pole again. And that kind of looks more like a heart, that one right there. So we look at these 4 graphs. How does a sine versus cosine? So we see that for sine, it's going vertical, up or down. For cosine, we see that it's going horizontal, left or right. We do see that if there's a positive trig function, if the trig function has a positive sign in front of it, it's going to be mostly above the pole. If you have a negative in front of the trig function, it'll be mostly below the pole, as we saw for the last graph. And that's true for the sine ones. For the cosine ones, mostly above or right. So I should have said that actually, or mostly below or left, because for cosine graphs, it's about left or right, obviously. So if you have a positive for the cosine, the graph will be mostly to the right. If it's a negative, mostly to the left. Okay, let's dig a little deeper. Let's take a look at 2 minus 2 cos theta. That was actually the second graph we did. Let's take a deeper dive here. So again, we'll go from 0 to 2 pi for theta, but let's change it to 0 to pi. Sorry, we did 0 to 2 pi, but let's go look at 0 to pi. And that will be the top half of the graph. So above theta equals 0 line, which is kind of like the x-axis in a way. Yeah, and so if I were to go back to that again, I think I still have it stored here. Nope, that was another one. My bad. So 2 minus 2, that was the first one. 2 minus 2 cos theta. But change that to pi for theta max. Wrap the sucker, and you only get the top half. And in fact, actually, I probably should expand that to, say, -6 and 6. There we go. Actually, I don't even know why I went all the way to 6, but 4 is good enough. So only get the top half. Now determine the zeros of this. So that's easy. You know, just set r equal to 0. Solve for theta. Cosine theta is 1. And cosine theta is 1. We know that at 0. Yeah, just at 0. Or 2 pi as well. So, or generally speaking, you can say 2 pi k, where k is any integer. But for our specific interval, definitely 0, 0 and 0, 2 pi. And then find the points where that graph crosses the line theta equals 0 and theta equals pi over 2. Well, of course, you know, just plug in 0 for theta. That's not hard. 2 minus 2 cos 0, which of course will be 0. which we already have. We already know this. Or for the other one, if you plug in pi over 2 for theta, cosine pi over 2 we know is 0, so r equals 2. So that would be 2 comma pi over 2. Excuse me. Also, you could take a look at what happens when theta is pi or 3 pi over 2, all those things. And I did that already. I already did a table when we did this. And that should help in generating the graph more accurately and kind of see the little divot that happens in the cardioid. Let's move on to the next page. So what we're into values from 0 to 2 pi produce a part of the graph that is to the right of theta equals pi over 2. Where theta pi over 2 kind of looks like the y-axis. We don't call it that in the polar coordinate system. So if we carefully think about it, we had a point at 2 comma pi over 2. We also had a point at 2 comma 3 pi over 2. So again, our equation is r equals 2 minus 2 cos theta. If you plug in pi over 2, we got 2, and likewise at 3 pi over 2. So, and then again, there's a little divot that happens there. So clearly to the right of theta equals pi over 2, what range of values for theta produce that? Well, clearly between pi over 2 and 3 pi over 2. And that's just by looking at it. But when you're actually producing it, you don't really, there's also some parts between, actually, let me take that back a little bit. That actually doesn't make sense what I just said. Initially, from 0 to pi over 2 produces the upper portion of that curve that we see right now. And then 3 pi over 2 to 2 pi produces that lower portion. So that produced this, that produced this. Yeah, because obviously from pi over 2, 3 pi over 2 is the left side, so that didn't make any sense. So that's what produces it. State the symmetries. Well, that's not hard. Remember, if you want to be symmetric about theta equals 0, which we know from the looks of it, right? Then we could try r negative theta. That was from the previous lesson. So replace theta with negative theta and see if we get the same thing, which you should, because cosine is an even function. And there you go. So that verifies that symmetry. And generally they have the form of r equals a plus b cos theta, or r equals a plus b sine theta. And we saw that for the stuff we did earlier as well, when we had limicons that had the little loops that had them. And for limicons, we noticed that the constant they were adding to the trig function, the absolute value of that was less than the coefficient of the trig function. Here we're noticing kind of the opposite, right? We're noticing that the constant is greater or equaling. Actually, in this case, every time the constant was actually equal to the absolute value of the coefficient of the trig function. That's one thing we noticed here. Because we have 1 plus cos theta, 2 minus 2 cos theta, 3 plus 3 sine theta, 4 minus 4 sine theta. So now we're going to look at other types. Dimple limicon curves and convex limicon curves. So before I do the graphs, just so you know, the left curve is what we call a dimpled limicon. And the right one will be what we call a convex limicon, because it won't cave in. And again, generally speaking, we're talking about A plus B cos theta, y equals A plus B sine theta. And for limicons, we had this going on here, right? The upside of A was less. That's for a limicon. Where for the cardioids, we had this. The upside of A equal to upside of B. But what if the upside of A is greater than the upside of B? And more specifically, what if the ratio of A would be the absolute values between 1 and 2 are greater than or equal to 2? So if I were to graph this one, again, just punch into Desmos or graphing calculator, it's going to kind of look like that. It has a bit of a dimple. And the ratio is 4/3 between A and B. Here, the ratio of the upside of A and B is 5/2. And it'll be flat up here and kind of look like that. And this is most likely, as you probably guessed, -7. And this right here would be 3, I think. And these would be a 5 and -5. And then here, probably your guess is probably at -1. This probably be at 7. This would be at 4 and -4. If you work those out. Because remember, cosine of pi over 2 is 0, cosine 3 pi over 2 is 0, but cosine of 0 is 1, 4 plus 3 is 7. So not hard to figure out where they're touching all those different axes. Okay, let's move on to part B. Okay, for part D, other polar curve symmetry about the pole. So here we have something called a lemniscate. So we're going to set our window to the following. And then we're going to generate these graphs right here and describe them. Give me one sec. Okay, so let's take a look at the lemniscate. So let's fix our window here. So we're going to go from -2 pi to 2 pi. And 2 pi. We're going to go from -4 to +4 for x, and -3 to 3 for y, which I already have. And then we're going to graph r squared equals 9 cos 2 theta, but you're going to have to put as two different equations. So the root 9 cos 2 theta. And that's negative counterpart. Negative root 9 cos 2 theta. So it looks like kind of like a dumbbell in a way, if that makes sense. And then if I do adjustment to the other one, let's make that 16. So you see it's going to be a little bit wider. And there you go for that one. So let's go ahead and put this into the polar curve here. So it looks like it reached a radius of 3, which makes sense because if you plug in like say 0 for, or sorry, pi over 4 actually for beta for the first one, you do get no, sorry, if you plug in 0, you do get 9, but r would be 3 or -3. If you do plug in pi over 4, you do get 0, so it does hit the pole. Excuse me. If you plug in pi over 2, that will be cosine of yeah, if you plug in pi over 2, it's 0. No, sorry, plug in pi over 2, you get cosine pi, which is -1, but that's kind of weird because r can't be negative clearly. Remember, this is the curve we got. And for the other one, we'll switch colors to green. You get that. So describe each graph. So obviously they're horizontal. They have horizontal orientation. I think that's pretty obvious. And how does A impact? So A gives the length of the loop. And it's from the center to the farthest point. So A gives the length of the loop. And replace cosine with sine. How will that look different? Let's go back to the calculator again. Oh, here we go. Replace that with sine. Replace that with sine. So it's interesting. It actually is reoriented at a pi over 4 angle. So that's how that would look. So let's actually scroll down here and go ahead and clear some stuff. Yeah, so again, it's oriented at a pi over 4 angle. So it will look kind of like this. Pi over 4, which also makes sense because pi over 2 is 1, right? So you have a r is 3 or -3. 1, 2, 3. And then 5 pi over 4. You stretch it out. You get 16 for a squared. And what values do you get when you plug in pi over 4? I mean, obviously it's pretty easy, right? 9 sine 2 times pi over 4. You have sine pi over 2, which you know is 1, equals 9. So r is plus or minus 3, right? So that's we have 3 comma pi over 4 as a point, and -3 comma pi over 4. Which would be in the other direction. And so they're right here and here, as you kind of see. I just drew those in. And I don't think I'm going to finish up all these notes today because this is going to make this video way too long. And I'll talk about rose curves with you guys when I'm back on campus on Wednesday. Let's take a look at F. So this has a special symmetry, like the function y equals x cubed. Recall y equals x cubed symmetric about the origin. We know this, -x, -y. So the polar curve is symmetric about the pole. In other words, if you turn it upside down, you get the same image. Notice that 3 pi over 4 is on the curve, and the point -3 pi over 4 is also on the curve. So if r theta is in a curve, then negative r theta or r theta plus pi, if you do 180-degree rotations, also on the curve. So thus we have this kind of symmetry happening. We're symmetric about the pole, just like how, like for rectangular coordinates, you're symmetric about the origin. And to show that algebraically, we'll try negative r theta. So if you replace theta with theta and replace r with negative r, you wind up getting the same thing, right? To get back to the original. So that implies you're symmetric about the pole when that happens. And remember, to be symmetric about theta equals pi over 2, it's got to be negative r and negative theta. To be symmetric about pi over 2, which we would see for the limicons that had sign in them. We saw that. But remember, for the or if about theta equals 0, that was r negative theta. Sorry, that was a little different. That was r negative theta for symmetric about theta equals 0. But about the pole, it's going to be negative r theta. That's the symmetry due for pole symmetry. So we'll summarize all this when I'm back on campus about all the different symmetries you could see, because it is a little confusing. There's symmetry about theta equals 0, which is going to be r negative theta. And then about this is theta equals 0 symmetry. This is theta equals pi over 2 symmetry. And about pole symmetry, it's going to be negative r theta. But we'll again summarize all this when I'm back on campus. Let's just take a look at part G. Think about answers the question E, how would you change the function so that it is diagonal going down from left to right instead of what we have from right to left. So you want about theta equals pi over 4. So drawing a polar system here, you only symmetric along that line now. About theta equals 3 pi over 4. So what you could do is you could do something like this. R squared equals 9 sine, and it's going to be kind of like a horizontal shift or transformation. You rotate 90 degrees, basically. Or this will work too. So, oh yeah, the summer's down here. There we go. So to be symmetric about the polar axis, which is theta equals 0, we need r negative theta. Or you could think of it as negative r pi minus theta. Or here, you could do negative r negative theta. Or you could think of it as r pi minus theta. Or here, you could think of it for the pole, which we just did, negative r theta, or rotate 180 degrees, theta equals r theta plus pi. That's how you can take a look. Now, the one thing is that this is true when you go up to 2 pi for a complete revolution. You're not going to see the symmetry if you're not doing a complete revolution. So that's just something to think about. Rose curves, I really don't want to get into. I think this video is pretty long, and I don't want to overwhelm you guys with too much homework, especially for our Warpole boys. We will begin NorCals tomorrow. Good luck to you guys. I know there's going to be some long travel if you guys get far and have to go to Stockton. And other sports too. I know there's other stuff going on. Other sports are ramping up, or other things are going on in life, other tests. So don't want to make this too long. I could finish off rose curves pretty quickly when we see each other in person on Wednesday. And this lesson here, part 3, I think it's pretty short. Yeah, so I could totally knock out the rest of the part 2 and part 3 on Wednesday, and then part 4 we'll do on Friday. So we should have the polar unit all done by Friday. Homework is going to be pages 3 and 4 of handout A. Now that you can do these type of curves, because we just talked about them. And then definitely you could do this stuff here as well. Handout B. That shouldn't be a problem. That's Millennium skates. I'm not going to do 3 because that's rose curves. So we're not going to do pages 7 and 8. Page 6 looks like that's on the dimpled limicon. Again, taking a look at number 2, and I do have the solution key for this actually, which is right here, which I'll share with you guys. Nope, that's the notes. Hold on a sec. Oh, that is handout A solutions. There we go. Yeah, so taking a look at this. Yeah, you have 1 minus 3 cos theta. So that was a limicon. I'll share this so you guys have access to this. And then two is a rows. We're not ready for that yet. Actually, I'm not going to assign that. Never mind. So yeah, so definitely homework will be pretty short again. We'll do rows curves tomorrow, not tomorrow, Wednesday in class. So homework will just be work on handout B, pages 5 and 6 then. So yeah, homework would be pretty short. You can probably knock this out in class today. But pages 3 and 4 of handout A, yeah, I haven't talked about rows curves yet, so let's hold off on that. I know it looked a little funny to me. And then pages 7 and 8 of handout B, also we'll hold off on that. That's also more in rows curves. We're going to talk about rows curves in class on Wednesday. And then we'll do part 3 of the notes, which I believe connects to conics, if I'm not mistaken. Yeah, connects to conics. So we'll have that discussion as well in class on Wednesday. And then, of course, homework for that will be handout C, which is all right here. And then we'll work on a handout D in class on Friday when we finish off those notes. So we still got a lot to do. And the goal is to try to get all done before Thanksgiving break and then do a review when we're back from Thanksgiving. All right, looks like we're all set. I'll see you guys later.